We did this on Friday, but here's the lecture. Um, we went through these slides pretty quickly at the end of the chapter, so I'm gonna put these up and try to get caught up a little bit. Defining the system. We talked about this briefly. I suggest you read this section. It's not too earth-shattering stuff, but it's important nonetheless. We talk about systems when we're dealing with engineering. A lot of times we have a particular part or a particular property or something like that, or a particular substance that we're interested in measuring or monitoring. In this case, this is showing a picture of a flume down in Boise, Idaho, that is used for testing water flow of all sorts. And this is an artificial channel for conveying water. That's what a flume is. And so in this system, the water flow is of interest. We might be flowing this water over some soil or or to simulate some river flow, or it might be dam operations or all sorts of things. But that would be our system. Our system would be the water. The surroundings in this case would be the surrounding atmosphere inside the flume chamber. And then what's really important is understanding what the boundary conditions are. And that's just going to depend on the type of problem that we're trying to solve and look at. And we know in fluid mechanics and also other types of engineering problems, boundary conditions are quite important. And that will be true in fluid mechanics as well in this course. So systems are described by specifying quantities that characterize them. And in particular, we're interested in this chapter and in engineering in general in looking at properties. And properties, a property is a measurable quantity of a system that depends only on the present conditions within the system. So in the case of the flume, we might be measuring water flow continuously throughout this experiment at a certain time interval to determine what the properties of that water are as a function of time. The state of a system describes the conditions of the system by specifying various properties. And the change of a system from one state to another is called a process. And engineers like to name processes. I think that's the next slide, actually. I'll get to that in a minute. In the case of this cylinder, the system that we're interested in is going to be the air inside the cylinder. And basically the surroundings are going to be the chamber in which the air or the gas is being held. And we're going to impose basically a pressure on this by pushing the plunger down. And what's of interest to us are the pressure, temperature, and volume of the air before the compression and after the compression. And so the state of the system has changed from state 1 to state 2 before and after the compression. And the properties, pressure, temperature, and volume, have changed as a result of the plunger compressing the air. So it's just kind of an example of how the terminology that we use in engineering and science to determine to define a system. These are just a couple of processes that have titles. An isothermal process is one that occurs at constant temperature, where the temperature is held constant. And an adiabatic process is one in which the surroundings are not allowed to have any heat transfer. So it's like an insulated process where there's no heat transfer in and out of the system. So we'll use this terminology at times throughout the semester and throughout the book. And that's the reason why the book defines these terms, but primarily what we're interested in in this particular chapter are the properties. We're going to be defining properties of fluids that we need to proceed to understand fluid mechanics. So let's start with mass density. We all have a pretty good image of this. It's just the mass over the volume. And this is very interesting. I found this very interesting that this, remember when we talked about the continuum assumption? If we actually take the limit all the way to the volume being 0, then we start to invalidate the continuum assumption. So I would maintain that actually in fluid mechanics, we don't want to take the limit as the volume goes all the way to 0, but we do want to take the limit as the volume gets small. Whoops, sorry, I'm not sure why my pen's not working. Why it gets small, not 0. Otherwise, it would invalidate the continuum assumption that we talked about. The units are in kilogram per meter cubed, and traditional units are, as we know, slugs and foot mass or pound mass. Sorry, are in our units of mass. So these can either be slug per foot cube or pound mass per foot cubed for traditional units. Density is this is a chart showing the density of common fluids, and we can see water here at a couple of different temperatures. I did want to mention that you can see that the density is a little bit less for water at 90 degrees than it is for 4 degrees. And in fact, it goes down by about 3.5% in that 90 degrees, or that, almost 90 degrees. And so that's when the water is heated, the density drops a bit. Also, you can see that most fluids, at least a lot of fluids that we show here, from maybe here up, are within just 30%, even this one maybe not quite, but these fluids are all within 30% of water, and that is true for most liquids, but not all. A notable exception, obviously, is mercury. Mercury is a liquid, and it has a much higher density. You can see there's a break in the scale here, and it goes up to 13,500. So, but most liquids have a density within 30% of water. Some liquids have a lower density, as you can see. We've got oils and alcohol and gasoline here, and of course this makes them lighter, and so they we'll see when we talk about fluid statics that they actually float on top of the water. Okay, and one thing that I want to say is that in SI units, it's probably worthwhile memorizing that the density of water of H2O is about 1,000 kilograms per meter cubed. And in fact, I think that's a definition in the SI units, that's something that they've defined. And in traditional units, trad, the density of H2O equals either 62.4 pound mass, lbm, over foot cubed, or almost 2, or 1.94 slug per foot cubed. So you can see that factor of 32.2 coming in the different densities, depending on what mass unit you're using, either slugs or pound mass. So this is just a chart of how the density of water looks, what it looks like, and you can see that here we have ice, and as ice warms up, the density drops a little bit, and then as soon as the phase change occurs, as soon as it melts basically from solid to a liquid phase, this would be where the fluid takes over, we get a very a drop off of about a couple percent, from 1,000 down to about 960. So if you get to warm temperatures in water, you will have to deal with the fact that the density drops off. But if you're dealing with things right around here, around 0, around freezing or slightly above, you really don't need to worry about it. 10 out of 1,000 here is a pretty small fraction. Note also that water's kind of interesting, that right after the phase change, the density is actually the highest at 4 degrees C. It's actually not, this is a blow up of the curve right here, and you can see that the density actually peaks just after 0 and goes down. That allows some pretty interesting phenomenon. Okay, so that's density. Specific weight is the weight. Instead of the mass, it's the weight over the volume. And again, I would caution you that if we let our volume go to 0, we're probably violating the continuum assumption. But in any case, we're not going to worry about that. Gamma actually has a factor of G in it. What are the units? You can figure that out. In SI units, we've got kilograms per meter cubed over our times meters per second squared. So these are going to be the units. You could actually combine these guys into a Newton, and you're going to have a Newton per meter squared, which actually looks quite a bit like a pressure force per unit area. Did I get that right? Yes, I did. So it actually has pressure units. One other thing that I want to mention is just in SI units again, gamma of water of H2O equals about 9,800 Newton. Oh, this is a cubed. It's not. It's pressure over. Yeah, I knew there was something wrong. So this is a pressure units per length, basically. So it's Newton per meter cubed. I apologize for that mistake. And then in traditional units, DRAD, we've got gamma of water equaling 62.4 pound force over foot cubed. And this is obviously independent of slugs or mass because it's kind of built into the force. So another point here is that another property is the specific gravity, which is the basically the density of a fluid, of a liquid, relative to the density of water. And so this is just going to be, this is not going to have any units because you can see it's density over density or gamma over gamma, and either one. And so these are going to, the units are going to cancel out, and the units of specific gravity will be unitless. It's a unitless number. So I wanted to, in the book, they do an example. I just wanted to do that really quickly. I'll just start a new sheet here of looking at what and we talked about this in class. I asked you this, but let's just show you, whoops, mercury. This is going to equal the gamma of mercury, or the density of mercury, divided by the gamma of water. And the values of this are, the gamma of mercury is 133,000 Newton over meter cubed, and the gamma of water, as I showed you, was about 1900? Yeah, 1900 Newton meter cubed. The units cancel out. It should be unitless, so I've dealt with my units. I can deal with my numbers, and I get about 13 and a half. And so what this means is that the S of mercury, this is the chemical symbol for mercury, so I don't have to write mercury all out again. Sorry. The gamma of mercury equals about 13.5. It's 13 and a half times as dense as water. All right? So those are 3 fluid properties that we're going to be interested in: density, specific weight, and specific gravity. Engineers need to decide how to handle the density of fluids. Are we in a situation where the density is going to be constant or variable? Quite often in this class we will be having problems that will be constant density, but not always. And when can we make this assumption? Most of the time we will be able to make the assumption. And so this gets us into kind of two topics. And one is the topic of compressibility, and the other topic is the topic of constant density. So make sure that you understand that those are two separate concepts. So we're going to first talk about the bulk modulus of elasticity, which is used to describe the compressibility. And this is the equation for the bulk modulus. It's a change in pressure, dP, over a fractional change in volume. So this is basically a delta volume over divided by the volume, which gives us a fractional change. So why do you think there's a negative sign? Why physically would they just define this such that it's negative? The reason is because when you take a fluid and you apply a pressure to it, the volume, the fractional volume change decreases. So for an increase in pressure, you get a decrease in volume. And so they add a minus sign there so that the bulk modulus is a positive value. So that can be kind of confusing. Remember, if you're ever using this equation or having to calculate it, that you include this minus sign, otherwise you get the wrong sign. In fact, the bulk modulus will be negative. So remember, one way to remember this is to obviously remember the physics. A change in pressure causes a decrease in the volume. Or just remember that this it always needs to be positive. Okay? So we're going to do an example of looking at the compressibility of water versus air here in a minute. The bulk modulus for water equals, for water, has a value of 2.2 billion Newton meter squared. Those are in pressure units, note. And that is a positive value. And this implies that, as the book suggests, that the fraction change in volume is about a 1/20th of 1% for a pressure change of 10 atmospheres for dP of about 10 atmospheres, ATM atmospheres. Now this is a tremendous change in pressure. I'm like, 10 atmospheres, boy, that seems like a lot. Remember that one atmosphere is equal to atmospheric pressure at sea level. The types of pressure changes that we see normally day to day in the atmosphere, or say as a low and a high pressure system come through our area, is about 10 millibars, which is about 0.01 atmospheres. And so 10 atmospheres is 1,000 times this. So for a pressure change of 1,000 times what's occurring kind of on a weekly basis in Moscow or Pullman, we see that we have only 1/20th of a percent of change. So this is just, very, very small. Water is not going to change very much under normal pressure conditions. You'd have to really squish the water. So what this means is that water, H2O, and therefore most liquids, because they have a similar density, most liquids are assumed to be incompressible. So this is a nice simplification or assumption that we can make in fluid mechanical calculations. Now, this is not true for gases. So gases are compressible. So whenever you're dealing with a problem using gas, you're going to have to deal with this. So for an ideal gas, we have a couple of different situations, and in some cases we'll have to deal with this. And so it turns out that the bulk modulus of elasticity for isothermal processes can be shown to be proportional to pressure. So if you have a situation where the pressure is changing in the gas and you're trying to understand, say, how the gas is flowing, you're going to have to account, you might have to account for the fact that the compressibility or the bulk modulus is changing. Now for adiabatic processes here, again, these are processes where there's no heat exchange within the system, between the system and its surroundings. For that situation, we have an extra factor in there, the ratio of specific heats that multiplied by the pressure. Now I can't think of any problems that we did where we use this. I'm not saying we won't this semester, but this is something that we are normally going to be assuming that our fluids are incompressible in this course. But of course, they may not be, especially if you're using gases. A lot of times with gases, you'll have to deal with it. So now let's switch to the topic of constant density, okay, which is a kind of a related but a separate topic. In general, most fluids have a high value of bulk modulus, so they can be assumed to be incompressible. Oh, yeah, there's one other thing there's one other topic that I want to say, that I want to do before I move on to constant density. So let's go back to the bulk modulus. I wanted to show you the example in the book. The example in the book compares air and water. If you remember, I wanted to do that back here. I'm going to show you a comparison of the bulk modulus of air and water. So let's go ahead. We know that the bulk modulus is equal to this, minus dP over d volume, fractional change in volume. We can kind of approximate that by saying a change in pressure over a change in volume over volume. And so we can rearrange this equation to look at the fractional change in volume. Okay, and this is actually what we mean by the compressibility. So this is going to be the change in pressure over the bulk modulus of elasticity. So this is what we call compressibility. The compressibility is not the bulk modulus. The compressibility is what happens. I'll just say compressible. This is what we're interested in, the fractional change in the volume as it's applied to the pressure. So this is what we mean by compressible. If this fractional change is small, then we can assume that the fluid is incompressible. So what we want to do now is we want to compare, as is done in the book, we want to compare the compressibility of air. So we want to compare of air over that of water. So let's see how much more compressible air is than water. And so if we write this down, we have, in terms of the equation, we're going to have this situation, air over minus dP bulk modulus of H2O. And we can see that for the same pressure change, if we exerted the same pressure change on the air as the water, that these terms are going to cancel out, as well as the minus signs. And what we're left with is this kind of strange equation that just appears in the book of this over 1 over EV H2O. And of course, if we manipulate things around a little bit, we get that we have the bulk modulus over of water over the bulk modulus of air. So the equations turn out that if we want to know the fractional change, let me get my pointer, with fractional change, the compressibility of air over the compressibility of water, that actually equals the bulk modulus of water over that of air. Just the way the equations work out. So that turns out to be 2.2 times 10 to the 9, as we saw before. That's pascals, Newton per meter, or Newton per meter squared. And the bulk modulus for air is 1 times 10 to the 5 pascals. So this equals 22,000. So what does that mean? It means that the compressibility of air is 22,000 times that of H2O for the same pressure change. If we go back, this is what we were calculating right here, air over water. That factor is 22,000. So air is 22,000 times more compressible than water. So in a lot of situations we can assume water is incompressible or liquids, but in many situations we will have to deal with the compressibility of gases like air. So let's now move on to talking about modeling fluids as a constant density. And in general, fluids have a high value, liquids do have a high value of bulk modulus, and they can be assumed to be incompressible, although in many situations gases will not be. Incompressibility means that the density for each fluid parcel is independent of pressure. That means if the pressure is changing, it's not going to change the volume, and it's not going to therefore change the density. But a fluid that is incompressible, this is the key point here. A fluid that is incompressible can still have a variable density. So water or a liquid, you can move from one place in the fluid to another place in the fluid, and the density may change. It's a little hard to imagine that, but that is the case. Sometimes we have to account for that. So for gases, it is also common to assume that they have constant density. This is not because the bulk modulus is small, but it is rather common to assume that pressure variations within a gas are small. So this is the key for gases. We can get around this issue of constant density. We may have to deal with the incompressibility, but we can assume that the gases are typically constant density because the pressure variations are small. So the volume may be changing, but if the pressure changes are small, then the bulk modulus isn't really changing much because the pressure change is small. So for gases, and I think I misstated this in class. I think I misstated that the Mach number was used to determine incompressibility. It's not. It's used to determine whether or not we have to deal with constant density. So make sure you note that I may have misstated this in class. So to distinguish constant density from variable density, we use the Mach number. And basically, I think this is because this is the velocity of the flow over the speed of sound, and that when we get up to a large Mach number, a Mach number of greater than 0.3, that the fluid is so turbulent that we get pockets of higher and lower density variations. So this is the criterion for idealizing a gas at constant density. So if you ever come up against a situation where you're wondering whether or not you can assume constant density, you can calculate the Mach number and determine if it's less than 0.3. If it is, then you can be assured that you can ignore this effect. Now, obviously, another reason why we may not be able to, when we do not meet this criterion, what's probably going on is the pressure variations across the gas are so high that we're probably inducing a lot of volume change. So I mentioned that I thought the ideal gas law was a little bit misplaced. I've added in the notes, I've kind of edited the notes here to add this table again to remind you of what the ideal gas law is. Remember that we're most interested in the density and the mass forms of this equation. So this is just for your knowledge again. And then I also listed here the conditions for validity. And remember this one here, when the gases get very hot, we begin to invalidate the ideal gas law. So we're really in this situation with gases where they are compressible. We know that because we can see that whenever there are pressure changes, and temperature changes here, the volume could change as well. So volume is in the density, and volume is here as V bar. So we know that gases are compressible. Usually, liquids are not compressible, and that we have the situation that when gases get really hot, the ideal gas law is invalid, and that if we if we get velocities that are over this threshold, if the Mach number is over this threshold of 0.3, we're going to be in a situation where we're violating the constant density assumption. So the final thing that I wanted to do in this section of notes was to just say really briefly what is good practice for finding fluid properties and documenting them. And so this is a very short section in the book that just gives this list here, but it's very good when you're doing problems to list the name of your fluid, list the temperature and pressure at which the property was reported in your documentation, in your source, and cite the source of the fluid property in your documentation. So you can see down here, it's the source for this is table A3. It's air at 20 degrees C and 1 atmosphere. It's listing the temperature and pressure and also the source of the documentation. List the relevant assumptions that went into it. The assumptions are that the air has a constant density, and list the value and the units of the fluid property which we have here. And be concise, write down the minimum information required to get the job done, but make sure that you document your where you get things from. So what I'm saying is that it will be important for you to have information like this, minus the blue stuff, this stuff in here, on your homework, so that we know where you got the information from. This is critical in engineering. It's not okay to just pull values out of the air. If you work for a consulting firm, you never know when someone might come back and need to look at your documentation. It could actually be a legal situation. So your company might be legally bound by your engineering documents. So it's very good to have documentation of how you derived your equations, so that if necessary, you can prove that you did an adequate engineering job. So this is not a trivial thing. It's a very important thing in engineering practice. So I believe that's it. The next set of notes will start with section 2.5.